Good noon to one and all. I welcome you to RSD 2021. RSD, or Research Scholars Day, is an annual research festival of IIT Madras. We aim to bring together ingenious minds while encouraging free exchange of ideas and research interest by organizing lectures by eminent speakers, workshops, research expos, and wider range of competitions. After the wonderful day one session of RSD 2021 yesterday, we welcome you back to day two of our fest. It gives me great pleasure and honor to welcome our speaker, Dr. John Phillip, to another exciting lecture session of RSD. Thank you for joining with us, sir. Dr. John Phillip is working as a scientist at Indira Gandhi Center for Atomic Research and also professor at Homi Bhabha National Institute. He leads the Smart Materials section and Corrosion Science and Technology Division of Metallurgy and Materials Group. Sir obtained his PhD from IIT Madras and did his postdoc at CRPP CNRS, France, and University of Hull, UK. Sir has received many notable awards and recognitions, including Science and Technology Excellence Award in 2006, INS Medal in 2007, Distinguished Faculty Award of Homi Bhabha National Institute in 2015, and the list goes. Currently, he is listed in the world's top 2% scientist list by Stanford University, US. Today, he is here with us to speak on smart nanomaterials and their applications. Over to you, sir.
Very good morning to one and all. First of all, I would like to thank the RSD team and the IIT Madras for having me as a speaker today. It's an honor and privilege to be invited by the alma mater. I would also like to congratulate the RSD team for organizing such a fabulous event by bringing in experts from diverse disciplines, and I'm sure it's a buffet for the participants, and it's my pleasure to be part of this. So without wasting much time, I will move on to my lecture. I will share my PPT. Is that okay? You are able to see the PPT? Yeah.
Yes, sir.
Audio is fine? Audio is fine?
Yes, sir. It is fine, sir.
Sir, we are
Right.
hearing some background noise. Possible if you use an earphone.
You are getting background noise?
Yes, sir.
What about now?
Yes, sir. It's better.
Arnav?
It's better.
Is it okay?
Yes, sir.
Yes, sir.
It's better?
Yes.
Yeah. Okay. So the title of my talk today is Smart Nanomaterials and Their Applications. The first question is, what are smart nanomaterials? In the previous speaker talked about smart materials and smart technologies. And all of you must be familiar with the nanomaterials and nanotechnology. You know that the materials with a dimension ranging from 1 to 100 nanometer, which is called nanoscale, are called nanomaterials. And what are smart nanomaterials? We always get inspiration from nature. We are trying to mimic what nature has been doing for millions of years. So I start my example with an example. I start showing an example from nature to explain what are smart materials. All of you must have seen this plant. It is called touch me not, or botanical name of this plant is Mimosa pudica. What is special about this plant? Leaves fold inward and it reopens after a while. It's not only touching. Sometimes you shake the plant and in the afternoons you see that this plant leaves remain closed. This is a mechanism of defense from predators to evaporate water vapor from the leaf. So what is special in this case? the plant is able to sense various stimuli. What I refer to stimuli is general touch or vibration or the temperature, and they are able to respond to these stimuli. There are materials around us, for example, the piezoelectric materials. When you stress it, it produces a voltage or vice versa. You're also familiar with shape memory alloys, where the materials can change its shape and remember it. And when the stimuli is removed, in this particular case, what you're seeing is it is heated, it is bent. And when the heat is removed, it is again back to the original shape. We also have chromogenic materials which changes its color. For example, the photochromatic glasses that we use. With the sunlight, the transparency of this glass is changing. And the polymer chemistry, chemists and engineers are familiar with response stimuli polymers. These are the polymers that can change the conformation or the transparency. It can go from a transparent liquid to translucent or opaque, depending upon the conformation or the coiling of the polymers in the solution. So this behavior you can observe when you change the pH, when you change temperature or the ionic strength. These materials are also come under the category of smart material. Then again, there are some materials which can respond to a magnetic field and change their properties. For example, the magnetorheological fluids, which are used as dampers or vibration arresting applications. You also have materials that can respond to electric field and change their properties in a significant manner. So in all these cases, you have a stimuli or multiple stimuli and then change in the properties. The stimuli can be environmental, it can be chemical, it can be thermal, mechanical, electrical, or magnetic stimulus. With this stimulus, the properties that can be changed in these materials are the transparency of the color of the material, the size of the material, the shape of the material or conformation. In the case of polymeric materials, you have seen the volume of the material can be changed, viscosity, thermal or electrical conductivity, and so on. So materials that can respond to in a controllable and reversible manner and change some of their properties, physiochemical properties, are called smart materials. They're also called stimuli responsive material, or some people call it intelligent materials. So none of these materials you see any nano features or nano element. These are traditional materials. So the nanomaterials exhibiting similar response or responsible behavior are called smart nanomaterials. This talk is all about two such materials. I will show you the materials. We have been working on such materials, working with such materials for a very long time, almost 2 decades, and a lot of research students have worked very hard and obtained their degree. And also we have a lot of inventions on these two materials. These materials are prepared in our lab, and I will be talking about some of the results that we have from our lab. So the first material that you see here is a black fluid.
Excuse me, sir.
Yeah.
Sorry to interrupt, sir. There's a small bandwidth issue. Could you please switch off your video and speak, because it's
Right.
suffering a bit.
Okay.
Thank you, sir.
Okay.
Thanks a lot.
Yeah. Is it better now? Is it better now?
Yes, sir.
Yes, sir.
Yeah. Are you able to see the slide now?
Yes, sir. We're able to see.
Yeah.
Yeah.
Okay. Right. So, containing some nanoparticles. The black liquid that you see, it is at the bottom of the vial, but when it is placed between the pole pieces of an electromagnet, you can see that the liquid is drawn towards the pole piece remotely by controlling the magnetic field strength. So the fluid is responding to magnetic field and changing its properties. And this fluid you see is without magnetic field. That's the natural color of the fluid. It's an emulsion containing these nanograins of iron oxide particles. And when a magnetic field is applied, you can see the color of the fluid is changing. It's not only with a remote magnetic field. See, if you put a toy magnet at the bottom of the vial, you can invert them and the liquid will be able to hold its weight, like the one that you see here in this picture. And also, you will be able to generate all kinds of colors from this fluid by varying the magnetic field in a controlled manner. So this is a fluid containing iron oxide nanoparticles, and the size of the particle is around 10 nanometer. This is what I'm going to do. So now you can see a video here. So it flows like any other fluid, but I put a magnet at the bottom. Now you can see this movie. I'm able to invert the vial. The fluid retains and holding its weight. And when you remove the magnetic field, again the particles are disposed in the fluid. It's a perfectly reversible process. So this fluid is popularly known as ferrofluid or magnetic nanofluid in these days. So this fluid, you see that it is responding to a stimulus, which is the magnetic field, and it is almost like a liquid magnet with the liquid and magnetic properties. That is because of the suspended nanograins of magnetic nanoparticles. So typically, the size of the dispersed particle is less than 50 nanometers. The reason is that these particles, when you want to suspend in a fluid, they have to remain suspended. As you all know, this sedimentation velocity depends on the density mismatch and the size of the particle. Obviously, you can choose a highly viscous medium to delay the sedimentation of particle. That is what it is done in the case of magnetorheological fluids. Magnetorheological fluids, you have micron-sized particles, so they use very highly viscous oils to keep these particles suspended. And obviously, they also use rheological modifier. They are ferromagnetic materials. In this case, they are super paramagnetic materials. I'll talk about them. It's not only particles. These particles are to be functionalized with a layer of surfactant molecules to prevent aggregation. The nanoparticles are highly reactive. You know that a lot of atoms reside at the surface, and as a result, they are very reactive. They have a tendency to aggregate. This is one of the problems you face when you synthesize nanoparticle aggregation. If you want to prevent aggregation of nanoparticles, you have to provide a sort of sheath on the nanoparticles so that it may not be reactive. It may not react, or it may not come into contact. So you can have a sort of electrostatic or steric stabilization, it is called, to exert a strong repulsive forces between the particles when they come closer at nanoscales. So this is what you need. You need a layer of surfactant around that. You can see in this high resolution TM, you can see the amorphous contrast. That is because of the layer of surfactant or polymeric layer which is on the surface of this nanoparticle. This is called capping or functionalization. You can have different types of particles in this kind of magnetic fluid. It can be magnetite, Fe3O4, gamma Fe2O3, or cobalt, nickel, ferrites, that is mixed ferrite. And you can also dispose these particles in different fluids. It can be disposed in water, non-aqueous fluids like oil. And as I told you, size restriction comes from the fact that the particles to remain suspended and they have to be stable against strong dipolar interaction and aggregation. So to show you an example of or the importance of surface capping in stabilization of this kind of colloidal system, I have another movie here. So in the first movie, you saw particles captured with surfactant molecule, and the particle size is around 10 nanometers. If it is not properly functionalized, what happens to this fluid? That is what you see in this movie. So the size of the particle is exactly the same. The particles are the same, that is the iron oxide. Only difference is that the capping is not proper. The functionalization is not proper. Now you see the difference. The liquid is separated from these particles. Whereas in the other case, the liquid is not separating from the particles. So you provide mechanical energy to stabilize such particles. Even then you provide mechanical agitation. It may get dispersed in the fluid, but when you apply a strong magnetic field, then again they will cluster because they are like tiny magnets. So this is a unique material that has both magnetic and liquid properties. Now you have seen in the movie, the location of the fluid can be remotely controlled, or the particles or the fluid has an ability to conform to any geometry. And these fluids exhibit interesting properties, optical properties, thermal properties, microstructure, viscosity. And the size of these materials are comparable to bioentities. So you find a lot of biomedical applications for this material. And iron oxide nanoparticles are FDA approved material. And it is being used in MRI contrast, targeted drug delivery, and presently it is being tested for cancer treatment, and also it can be used for proteins detection, DNA separation. All these concepts have been demonstrated by various researchers. Now you see a second fluid, that's the emulsion. You see how this fluid is changing, the fluid is changed. These are structural colors. It is not the pigmented color that you see in paints and other displays. You can see it is a reversible process. When I increase the magnetic field, it is kept inside a solenoid coil, and I am slowly increasing the magnetic field. When I increase the magnetic field, you can see the color of the fluid is changing. So this is the kind of structural colors that you see in butterflies. In the case of some of the birds, they exhibit structural colors. Because of the nanostructures, they will be able to reflect one particular wavelength. This is what you see, the kind of colors in soft films, because the thickness of the film is nanoscale and it can reflect on particular wavelength when the Bragg condition is satisfied. The second fluid which is showing color, which is slightly bigger size, but we make it by using oil globules. Inside the oil globules, we put this 10 nanometer size particles, lot of these particles. So these particles are magnetically polarizable, and the particle size is so small the thermal energy is sufficient enough to keep these particles suspended in the liquid. That is what you see in this movie. You see the Brownian movement of these droplets, which can be observed under an optical microscope. That's the beauty of this system. The length scale is accessible like other colloidal system with optical microscope, and also the dynamics is very slow as compared to molecular or atomic system. This is the beauty of colloidal system. This is a colloidal suspension, but the size is very small, 10 nanometer or less. Now you see the microscopic behavior of the emulsion droplets when I apply a small magnetic field in the direction. So you see the structures are evolving, and still the structures are, they are moving in the liquid, and the structure is growing. You can see the structures are growing and aligning in on that direction, and the aspect ratio of the structures are increasing. So you see the order disorder transition can be manifested, and you can easily control the interparticle spacing within the fluid. That's the beauty of the system. And the beauty of the system is you can tune the interaction using a magnetic field. So what happens? It can induce a magnetic moment which is proportional to the applied magnetic field. That's what you see in this equation. And the magnetic interaction energy, again, you can tune it with a magnetic field. And the factor, the dimensionless factor which is used to explain the order disorder transition is coupling constant, which is the ratio of the magnetic to the thermal energy. So when this ratio is less than 1, you see Brownian motion of the particle. That's what you saw in the microscopic picture. The field is very small, but lambda is greater than 1. You will be able to see this kind of tip-to-tip aggregation because of the dipolar interaction, strong attractive interaction between the magnetic grains. And if you go to very strong field, you can see a thickening of the structure that is happening because of the lateral coalescence of these droplets. So that's what you have seen. The aspect ratio is increasing, and at some point you can see the size of the droplet because of this kind of lateral aggregation. So you have attractive interaction between the particles in the chain and the repulsive interaction between the chains. That's what it is. But if you go to very high field, you can overcome the barrier and bring them coalesce. That's what it is happening. So it is a wonderful system. You have already seen in the microscopy. Wonderful system to probe order disorder transition, which you cannot study in atomic system by using light microscopy. Obviously you can do it with the neutron and X-ray scattering techniques, but in this kind of system the length scales are comparable to the wavelength of light used. As a result, you can use light microscopy and light scattering techniques. I will also show you how these systems can be used to probe intermolecular forces. What I'm talking about is the piconewton or sub-piconewton forces acting between fine nanoparticles in a solution, which can be probed and manifested by using this kind of magnetically polarized. Now suppose you imagine that you have a polymeric material or surfactant which is used in stabilizing colloidal systems, and you need to know how they are interacting and what is the kind of interaction between the particles in colloidal system. This can be studied using this kind of system. You can also study the polymer surfactant complexation. This is again very, very important when it comes to practical applications, industrial formulations, which can be manifested by looking at the scattering and intermolecular forces. I'll touch upon this all this aspect in the next 10 to 20 minutes. Now look at the structural transmission, how it can manifest. You send a laser beam through this sample, you see the spot transmitted light intensity is disappearing and reappearing something, and then you would be able to see a ring-like structure. It takes little longer time. So I am increasing the magnetic field and laser beam is transmitted through this liquid, and you see the intensity of the transmitted light is decreasing, and then you see a pattern which is emerging, a circular pattern which is emerging, and this was the original spot. Originally the light intensity, the entire light was scattered, it is passing through the sample. Now with a very strong field, you see a spot is there. Around this spot you can see a ring-like structure. Why this is happening? This was quite puzzling. Why this is happening? When you increase the magnetic field through a fluid, nanofluid, you are seeing intensity reduction followed by a ring-like structure, and this ring-like pattern disappears when you switch off the magnetic field. So the person who was working on this problem was Junaid, and he wanted to understand what is happening. He changed the angle of incidence and looked at the kind of pattern which is emerging from this sample, and he realized that this is the scattering from the nanostructures that are formed in the fluid when the magnetic field is increased. To confirm this, we have taken a needle, a millimeter sized needle, and allowed this light to scatter from the surface. When the angle of incidence was very small, close to zero, we could see a ring-like pattern which is emerging. This we could see from an optical fiber of 100 micron. And in all these cases, what happens is the pattern is changing with the angle of incidence. See here, 20 degree, 45, and 90 degrees, see a straight line. Exactly the same thing you see when you change the angle of incidence with respect to the applied magnetic field strength in the case of magnetic field. So what is happening in this case is the scattering.
Sir,
Yeah.
I'm sorry to disturb, sir. Actually, your audio is breaking in between. So can we disconnect you and connect you back?
Yeah.
Yeah.
Okay.
Really sorry, sir, for interrupting in between,
Okay.
sir.
Okay.
Yeah, sir.
So I will stop sharing,
Yes, sir.
or I can connect my. Is it because of my audio?
Yeah, audio is breaking in between. So
So should I use a microphone and maybe separate?
Yeah.
Let me try that. No, is it better?
Sorry, sir. We couldn't hear you.
Okay, audio is better now.
Yeah, it is okay, but it's kind of breaking in between.
It is breaking in between. So what is to be done?
Yeah, it is okay now, I guess.
It is okay. Okay, so I can use my headset.
Okay.
I was using the laptop mic. Yeah. Now if you have a problem, you just let me know.
Yeah, sure, sir.
Okay. So what you see here is the scattering from the nanostructures which are formed. The structures are evolving in the magnetic field. That's what you see here, the transmitted intensity which is decreasing, and then it increases beyond some magnetic field. These are the critical fields that are required for the change of form in the entire volume, and then you see a kind of separate transition. All these things can be manifested beautifully from the scattered light intensity or diffraction pattern. You can even get information about the diameter of the structures that are formed. And you can find from the critical field the transitions or the field at which the separating transitions are occurring. All these things have been done, and there are 3 theses on this topic, and I wouldn't be able to talk about all these things. We have looked at the effect of applied field strength, particle size, dispersion properties on scattering. The beauty of the system is that the particle size is very small as compared to the incident laser light. That is the wavelength of light. And the primary particle size is around 10 nanometers. So you are in the Y region, and then when you increase the magnetic field, you try to form chains with the aspect ratio varying from 10 nanometers to several hundreds of nanometers to micron and even millimeters you can reach. So that's the beauty of the system. So all these studies have been done, and we have obtained a good amount of insight into the structures that are formed in the system and the kind of transitions that are taking place in magnetic fluids and so on. Now, one of the problems that industries are facing today is the short shelf life of products. What I'm referring to is the syrups, food and taste making stuff, the pharmaceutical products, paints, creams, polishes, agricultural sprays, and so on. In all these, you see, typically this is what it happens if you keep it for a longer time. These are dispersions, either salts or emulsions, multi-component systems, where you have oil droplets in water or particles dispersed in a fluid with some additives or stabilizer. Either they will cream it or sediment depending upon the density of these dispersed phases. When it comes to nanofluid, it's again a very hot topic today. The destabilization or phase separation of this particle is a big issue. That's the issue we face with all kinds of creams and stuff that we use in cosmetics as well as food industries. So again, this is a field which is familiar with chemists and chemical engineers. You know that the intermolecular forces acting between the colloidal particle decides the stability of compounds. It decides the aggregation phenomena and phase behavior, and this is what it can happen. It can cream it or it can sediment depending upon the density mismatch. So what is decided here is very strong repulsive interaction between the particles. If the interaction is very strong and the net force, that is the sum of the repulsive interaction, essentially it comes from the charges at the interface of this particle or the kind of stabilizing moieties that you sometimes can be polymer, where the interaction forces are steric. And obviously in all kinds of system you can see the van der Waals interaction at very small interparticle spacing. Typically, if you take a 200 nanometer size emulsion droplet, the van der Waals interaction or van der Waals force is effective when the separation between these particles are less than 10 nanometers. So what you need to worry is the long range repulsive forces. If it is not very strong, what can happen is the particles will be able to cross this barrier. This is the sum of these forces. The barrier height is high, then it's better, and particles will not be able to cross this barrier and reach the primary minimum. If it is reaching the primary minimum, you end up in a scenario like this: particles are flocculated or aggregated. If it is in the primary minimum, it's not a major problem. You can provide some mechanical nothing to get them back. So these are the different techniques that are used to stabilize the system. You can use electrostatic, steric or electrosteric stabilization by using surfactants or charges to stabilize this particle. In this case, And in this case, you have steric interaction by uncharged polymer or neutral polymers. You can also use diblock polymers like the one which is shown here, which will have a hydrophobic and hydrophilic part which one can anchor to the surface and the other can protrude in the solution. This is one way of stabilizing. And you can also use polyelectrolyte or neutral polymers with the surfactant, where you will have electrostatic interaction between them. Now the problem is, how do you probe this interaction? One of the elegant technique which is developed in 70s is the surface force apparatus, where you can probe the interaction forces between two microscopic surfaces, for example two mica surfaces, where you can control the spacing between within nanometers. Within an angstrom level, the most recent one you can control, and look at the interaction forces. This simple Hooke's law is applied here to get the force that are measured. So this is a beautiful facility when it comes to macroscopic surfaces. And the beauty is you can also functionalize the surfaces with the macromolecules and see how they interact and how the forces vary as a function of distance. You see, it is from 150 nanometers down to a nanometer. You can bring them and get the forces. You can study the hydrophobic and hydrophilic interaction. That's what it is demonstrated. And the steric interaction. All these things are done between 70 and 90. It has a lot of relevance with respect to stability of system, lubrication, you can wear, and tribology. This system is used. Another technique that can use to probe interaction forces down to 10⁻⁹ is the atomic force. It's again complex, but it's a simple system. The tip size can be of the order of few nanometers, and you probe the forces between a macroscopic surface, a molecularly smooth surface is required. This is another requirement when it comes to, the forces down to nanoscale. And here again, you can control the spacing and obtain the interaction forces. But in none of these cases, you can probe the forces between the colloidal particles which are suspended. So how do you measure the forces as a function of distance? You have seen that the force is always a function of distance, and at some distance there is repulsive, and at very short interparticle spacing it is attractive. And this is to be measured as a function of distance, and you have no way you can do that in the case of a conventional colloidal system. So here the liquid or the magnetic emulsion which I have shown, showing different colors, is very, very useful to probe such interaction. All you need to do is, if you're working with an emulsion, you have to incorporate some nanograins inside, so it becomes magnetically polarizable. And in this particular case, what we have done is the diameter is 200 nanometer and the grain size is around 10 nanometers. You put a lot of grains inside and make this magnetically polarizable. As you all know, these colloids and emulsions are thermodynamically unstable system, but you can make them kinetically stable by using some kind of stabilizers and use surface active species to stabilize them. And as you've seen in the video, initially they are random and there is no net magnetization. The dipoles which are randomly oriented within the droplets, they are super paramagnetic. And when you apply magnetic field, you can control the magnetic interactions. As you have seen, the magnetic interaction you can tune. That means you can control the interparticle spacing. If you are able to control the interparticle spacing, it is very easy to measure the force as a function of distance in this system, because this I can skip, because when it forms an undimensional array, what is happening, the net force is balanced. What is the net force I'm talking about? The forces due to repulsion and the forces due to attraction. Forces due to repulsion on the kind of stabilizing moieties that you use. It can be electrostatic, it can be steric or electrostatic, depending upon the surfactant molecule or polymer surfactant that you use. And the attractive contribution at very small interparticle distance is originating from the van der Waals forces. And the long range attractive interaction which you can control is the magnetic interaction, which you can compute for an infinitely long chains using this expression. And the magnetic moment is a function of the applied magnetic field. That also you have the information, and you can compute the van der Waals interaction. By using these equations, you will be able to get the interaction force, the net interaction forces. Now the problem that you face in colloidal system is the interparticle spacing. Again, you have a solution with magnetically polarizable emulsion. This video you see Bragg peak. This is the Bragg peak you see in crystals with the X-rays. X-ray scattering is because the interparticle spacing or the lattice spacing falls in angstrom. So you have to use an X-ray to get diffraction pattern or the scattering. So in this case, what is done is the droplet size is of the order of 200 nanometers. So you have a length scale which is comparable to the visible wavelength. So when you apply very strong magnetic field, you see a Bragg peak at lower wavelength. And when you increase the magnetic field, when you decrease the magnetic field, the distance between the particles within the chain is decreasing. That is what you are seeing here in a video. I'm just slowly reducing the magnetic field. You see the Bragg peak is shifting, and this is measured at a constant angle. So you see the interparticle spacing within the chain is decreasing, and at some point the force is not sufficient enough to keep these particles within the chain, and then it becomes totally disordered. So you don't see any Bragg peak in the system. So you see how you can tune the magnetic interaction and obtain the ordering in the system. And we have used this concept to study the forces between surfactant stabilized system. We have studied the forces between sterically stabilized system. Here the beauty is that if you have a polymeric system and the polymer is used to stabilize these particles, what can happen is the decay length becomes comparable to the radius of gyration of the polymer. That means you will be able to tell what is the molecular weight or the radius of gyration of polymer by fitting the force parameters, force data, experimental data. So you see here the force is 0.1 piconewton to 10 raised to minus 11 newton. That's the kind of forces acting. And obviously all these things are validated with other experiment and theoretically. And so this is a very well established technique to probe interaction forces at nanoscale. And we have also shown long ago that it can also be used to probe the polymer surfactant interaction. It's a very complex phenomena which cannot be probed by any other technique except small angle neutron scattering. It's an indirect technique. And you have to go to cryo-TM experiment. All this information you can draw by looking at the interaction forces. That's what we have shown here. The kind of interaction that leads to different kinds of structures and interaction forces. And we could match our experimental finding with the cryo-TM experiment. That's what you see in this case. The polymer surfactant interaction can lead to huge enhancement in stability of colloid. That's what it is demonstrated in this paper. And these fluids can also be used for sensing applications. The technique is very simple. When it comes to detection of analytes, what we need is sensitivity and selectivity, obviously, and the simplicity of the technique, and it should be cost effective. What we have demonstrated here is, you create an array of these particles. This can be done very easily with a magnetic field. and the magnetic field strength required in this case is not very high. It's of the order of 80 or 90 volts. This can be generated very easily with a toy magnet also. So when you create this kind of ordering, you have a brand peak, and now if you introduce surfactant, alcohol or other molecules into the system, what happens is the electrostatic interaction or the conformation of polymer, if you use a polymer to stabilize this emulsion droplets, then the inter-particle spacing, d-spacing is changing by delta lambda. So that can be manifested spectroscopically. All you need is a spectrograph. A pocket-sized spectrograph can do all the jobs. And if you convert this shift delta lambda, you calibrate it, and you would be able to see what the concentration of ions is. Here again, you have a question, you have an issue, which is the specificity. Obviously, you have to use molecules that are specific to a cation so that you will be able to get selectivity also. This is what we are working on. This is work done by a student, Mahendran, and he has done a lot of work to look at the sensitivity of these nano emulsions for detection of different cations, and he could achieve different levels of sensitivity by using different functional moieties. So one of the issues here is achieving 100% selectivity. When you have mixed ions, how do you detect? How do you say that it's you have silver and calcium 2+ ions? How do you say that what's the concentration? This is quite challenging. So we have to use specific moieties which will the ions, a specific ion will go and bind to that moieties. That is what it is required. It can be done, and we have also shown that it can be used for glucose sensing. This is again work of Mahendran. And you can also, as I told you, the conformational changes that are happening at the interface of a surface can be manifested. This is already demonstrated by Israel Ashili and many other groups using surface force apparatus. But surface force apparatus is a very, very difficult experiment to work with. And you take days, and you never know when you get a good result. It's a very complicated experiment, but it's a wonderful wonderful device to probe the intermolecular. And no other experiment and technique can match the kind of sensitivity you can get with the surface force apparatus. But this is a simple technique, the magnetic emulsion, and we call it a chaining technique, where if the polymers are adsorbed depending upon the conformational changes happening, for example, this case, it is a temperature sensitive polymer. And what happens when you change the temperature? That's what it is shown here. So we can easily say that this is the transition which is happening at 34, and it is collapsing, and initially it is stretch condition and it is collapsing, and this information can draw by looking at the Bragg peak changes. And it can also be used for detecting defects in the material, like what you see, the kind of defects from X-ray. You can image and get the information about the defect. That is what you see in this video. You can see a specimen with a defect, and a thin film of the sample is kept, and you will be able to see the defects in the form of a color pattern. That's what this is the region where the defect is present. So by using modeling along with the color pattern, it is able to quantify the kind of defects that is present. A lot of work is done. I don't have time, so I just take 2 minutes more to conclude, and I don't want to exceed my time limit, though I started at 12:15. I will not delay your lunch. So I just want to go quickly. And another area of interest using this magnetic nanoparticle is magnetic hyperthermia. It is an emerging alternate cancer therapeutic procedure. It is in the advanced trial in Europe and many other countries, and I'm sure this would be a cancer therapy in 5 to 10 years time, or even less. So the advantage here is you can target the tissues that you want, the cancer or tumor cells. And it can be done in a distal, through distal guidance, and tissue specificity is also possible to achieve. So this is the working principle. You have to find out the cancer cells, and you have to inject the desired amount of the nanofluid into the cells, and you can apply a high frequency radiation. Okay, it is like an MRI system. High frequency magnetic field you have to apply to around 100 to 200 kilohertz is the frequency, and depending upon the frequency of the applied magnetic field and the field strength, you will be able to generate heating in the tissues, and you can ablate the cells. That's the working principle used in cancer therapy. We are not working on cancer therapy, but we are looking at the heating efficiency of this nanoparticle, and we are trying to make a biocompatible nanoparticles in our lab. We have a setup, in-house developed facility to look at the temperature changes that are happening in the ferrofluids or the magnetic fluids, and look at the temperature changes in a remote manner using a thermal imaging camera. That's what you see here. With the increase in the magnetic field and duration, you will be able to see the center of this coil is getting heated up, and that's the temperature which is shown here. And I already one PhD a student has completed his thesis in this field, and second one is completing. A lot of work is done on the heating efficiency of this nanoparticle. Another application we are pursuing for the reactor is the dynamic sealant. I think Dr. Ramachandran talked about magnetic ball bearing. Magnetic ball bearing combined with ferrofluid sealant is an innovative idea, and this kind of sealant is used in many technologies. It's a technology which is developed long ago in 70s or 80s by NASA and some companies in US. Now this technology is used in many devices, and we have indigenously developed this technology, and it's being used in our reactor applications. So another interesting application is magnetic field guided the iron oxide nanoparticles with specific coatings like dextrans, PG, and all are FDA approved up to certain quantity. It can be used in inhaler. It can make an aerosol with the drug molecules, so that you can reduce the side effect associated with powerful drugs, and you can get localization of the drug molecules to the region of interest. This is what it is demonstrated by a German group in the year 2007, and a lot of work is going on magnetic field guided drug delivery. It's a very promising area, and researchers who are interested in this field should pursue this, and because this is something one can do it without huge investment or technologies. And we have also shown that this kind of fluids can be used for heat transfer applications, and this is what something a student has demonstrated long ago, that you can achieve something like 300% of enhancement, which is not possible with conventional nanofluids. This is all because of the effective heat transfer through the nanochains or particles in the fluid. That's what it is done. Almost 2 theses is done on this topic, and due to paucity of time I will not dwell upon, and those who are interested in papers on all these topics, they can contact me. So I conclude. I've taken 5 minutes more, but I think still the time is less than what I thought is, and I will summarize by saying that magnetic fluid is a wonderful model system to probe order disorder transitions, and you can probe weak forces between colloidal particles, And I've also shown you that molecular conformational changes can be manifested by looking at the dramatic changes that are happening in the system. And these fluids exhibit interesting optical, thermal, and rheological properties, and they have many applications. I've shown some of the application. Defect detection, it's something we have invented in our lab. We have also shown for the first time the analyte sensing. I've shown some slides. We have developed a dynamic sealing technology indigenously because it's a technology which exists, but we have evolved the formulations, and we have developed the magnetic trap and tested it on component for dynamic sealing. Cancer therapy, it's a promising applications of this nanomaterials, and we are looking at the heating efficiency of this nanoparticle. Probably at some point we have to collaborate with some institutions to take this forward, and we are working on this, and this is also a very good system for targeted drug delivery. And with this, I conclude my talk, and I thank the organizers once again for giving me an opportunity to present this work. And I thank all my students, and whatever I presented is the work of my students and some of the staff members. And I thank the collaborators and funding agencies, and some of the images which I showed in the first part of my lecture comes from Google. So I want to thank Google also for the images. And thank you very much. And I will be happy to answer your questions. I can delay my lunch. No problem. Yeah. Yeah. Hello. Hello.
No, sir.
Yeah. I've done. Hello.
Thank you, sir, for such an exciting and enriching session. Sir, can we take up some questions?
Yeah. Sure. No
Yeah.
problem.
Okay.
Was there further interruption or?
In between, but it was okay, sir. We were
It was
able
okay.
to,
Yeah,
we were able
I'm
to-
sorry because bandwidth is an issue on holidays. Yeah,
Yes, sir.
yeah,
Yeah,
right.
that's it.
Yeah, I can take all the questions, no problem. I'll be happy to answer. Yeah,
Okay, sir.
yeah.
So one question was, how can we functionalize the surface of nanoparticles?
Oh, yes. Yeah. There are many ways. For example, we use some kind of fatty acids, this like oleic acid, for example. It binds to this iron oxide through some specific, binding mechanism. And you can also use small molecules, other molecule, fatty acid molecule, like, or you can use polymeric materials, because these are very, very tiny particles, so you cannot use big molecules, macromolecules. As I told you and shown you in one of the images, the particle size is around 10 nanometer, and the surface, the capping agent is around 1 nanometer or so. So you can choose. It's not universal that in all kinds of particles you may be working with gold or silver. So there are thiol molecules, and it's available in literature what kind of molecules you should aim to functionalize this molecule. And if you know the mechanism of binding, it is quite easy. And then you have to ensure that a monolayer of surfactant, which is at the interface of these nanoparticles, that is very, very essential for all kinds of applications. If you don't have a proper functionalization, the nanomaterials you prepare or nanofluids you develop will have no application. Obviously, a lot of people work with unstable fluids, and you can get all kinds of results, but none of these results will be reproduced reproducible by other people. And this is one of the biggest problem the nanofluid community is facing now. Many results that are published are not reproducible. That is because the nanofluids behave so differently. It is not only functionalization, it is also the monodispersity and the quality of nanoparticles. This is very, very challenging. When you prepare fluids or nanoparticles, and it should be fairly uniform. If the size is varying from 10 nanometer with a spread up to 50 or 60 nanometer, it's not a good system to work. The polydispersity should be as minimum as possible. That is what you need for practical application. Otherwise, whatever I have discussed today, the kind of applications I've shown for the cancer therapy, if you take it, say you go beyond 20 nanometers, say these are ferromagnetic materials. So you will have a residual magnetization. It's a problem. That is exactly the same case with condom dots or condom dots. For example, you can see beautiful color. Band gap tuning can be achieved. But when it comes to different sizes, the band gaps are different. When you put a lot of things together, what happens? Their behavior is different. Their properties are different. So you will not get any consistent result. The second problem is the aggregation of this particle. This is to be prevented. If the particles are aggregated and they are forming clusters, again the behavior of nanofluids. So it is a very, very challenging area. In general, nanomaterials, quality material, functionalization, and the monodispersion. These are the three things one should focus on. The good chemist can make it. There's no problem. If you are a good chemist, and you have to devote a lot of time, and you will be able to achieve very good monodispersity, and you can produce particles with a fairly monodispersed size. That is what it is required for practical application. So depending upon the system you're working, you have to decide what kind of molecules you can attach to the particle. I hope I have answered the question. Yeah. Yes, Rekha, go ahead.
Yes, sir. Thank
Yeah.
you.
Yes, sir.
Sriram.
Yeah,
Yeah.
yes, sir. Thank you, sir. Sir, can you tell us the growth of second generation solar cells with nanotech? I mean, how are solar cells?
Yeah.
cultured and
Yeah, so it is not connected to my work, but I can tell you the nanotechnology is finding application in almost all field. And for example, the solar cells, one technique which can be used is, some of the flies are able to see even under darkness or very feeble light. For example, moth, which is able to see. Why it is able to see? Now people have looked at the eye of a moth, and they found that nano bombs are there. It's about 100 nanometer diameter. Okay, so what it gives is it is able to concentrate all the lights. So that means the anti-reflective properties. So that kind of structures, if you can make it on solar cells and solar concentrators, what can be done is, you can make highly efficient. And people also use dye-sensitized solar cells, and a lot of nanotechnology comes into picture when it comes to solar cells or solar. And another problem that you face in solar cells is the dirt which is accumulating and it's bringing down the efficiency. As Dr. Ramachandra also told me, in our lab also we are working on super hydrophobicity. It's again an inspiration from nature, the lotus leaf. You wonder how the lotus leaf is self-cleaning its surface. It doesn't wet the surface. If there are dirt, it can be cleaned very easily if you put water. You don't have to apply. It's the super hydrophobicity, the contact angle greater than 150 degrees centigrade. That is why the lotus is able to self-clean it. So when somebody looked at the lotus microstructure under an SEM microscope, they found something very interesting. It has a hierarchical structure made with nano and micron scale features and wax crystalloids, which are about 10 nanometers, which are all around these rough surfaces. Micro nanoscale roughness, which is called a hierarchical structure. And now the engineering community is looking at developing super hydrophobic surfaces, and we have success. Not only us, everybody has success, but the problem is the durability. How long the surface is durable? You can pattern the surface by laser. You can deposit materials, nanomaterials at the surface, and make the surface super hydrophobic. If that is super hydrophobic, when it rains, all the dust is cleaned and you don't have to use any cleaning agent, and the surface always remain clean. And this technology can be used in solar cells and in a solar converter, solar concentrator. Again, the anti-reflective properties of materials can be used. So nanotechnology is finding application in almost every domain. For example, you always wonder how gecko is able to move up and down on the walls. Again, it has some nano features. That's the reason why it is able to climb up and down, and it can sit on the ceiling. That is because this very strong van der Waals attraction, it is able to generate between the surface and its toe, which contains millions of nanoscale fibrous hairs. And that is the technology now the engineers are trying to mimic, to create wall climbing robots which can work in hostile environment, high temperature, or in nuclear reactors. So nobody will be able to go inside because of the radiation. You can send a robot which can climb like a gecko, and that's the technology which is looked at. So in solar cells and all this field, you have some kind of nanotechnologies coming. In all these cases, you have some issues which are to be overcome, and which will be overcome one day, like any other technology. When piezoelectricity was discovered in 1880, no application for that. Now you see piezoelectric sensors everywhere. It is for the imaging, for lighting, diesel engines, and if you go to ultrasound scanning, it is used, and even your airbag is actuated by a piezoelectric sensor when there is an. So thousands of applications. And when you, as a student, when you invent things, you will find challenges. This is the challenge most of the scientists have faced. You invent something new and people don't accept it. This is what Michael Faraday, it happened. When he demonstrated electricity to the visiting prime minister, he asked, electricity, will it ever find any applications? He told, sir, one day you will tax it. This was the reply of Michael Faraday. Okay, so yeah, I think I've answered your question. Yeah.
Sir, Arnav, sir, I have one question.
Yes, Arnav.
I come from mechanical engineering background, so
yeah,
conventional machining, so a new domain has opened up, and we are using nanoparticle based coolants.
Yes.
Coolants and lubricants during the machining process.
Yeah.
So we may apply it in the form of a jet, or there can be some other form of application. Can you throw some light on that?
Arnav, your audio is breaking. Can you just be louder?
Hello, sir.
Yeah.
Am I audible now?
Now it is okay. Yeah. Can you repeat? I couldn't hear because it was breaking, your audio.
Yes,
yeah.
Sir. Sir, during conventional machining,
yeah,
there's one application of nano fluid.
Lubricants. Yeah.
Yes, as lubricants or coolants.
Yeah.
So
yes.
generally, we may apply it in the form of jet or some other form of application.
Yeah.
Can you please throw some light on the fluidic properties, like when it is being applied as a jet, how will it behave?
Yeah. See, this magnetic nanofluids which I have discussed today is a very promising candidate for such application as a lubricant, because if you have ferromagnetic component, because of the magnetism, it will be able to retain the thin layer of fluid will be remaining in curved and other parts. Okay, so this magnetic lubricant is already sold by some of the company for engine and other things, and also in lubrication it is used, magnetic fluids and other fluids, the magnetic fluid, other than magnetic fluids. If you consider the nanoparticles, I know that some of the nanoparticles, I think silicon carbide or some of the nanoparticles and nanofluids are used for lubrication purpose during machining. But there again you have an issue, which is the stability of these suspensions. Most of the suspension, unless you stabilize with an organic molecules, achieving very good stability or dispersibility is a problem. So in machining time, when you use if the temperature is very high, the stabilizing moieties can get degraded, and you will have issues. So this is to be overcome. It can be done in principle by using electrostatic. You can charge the particles and you can use it as long as the ionic strength and other solvent properties are controlled, and that kind of fluids are used. But very critical issue with respect to all kinds of nanofluids for practical applications, the stability, as I told you, the aggregation issues, and the long-term stability. These are the issues to be addressed. But magnetic fluid is very, very useful thing for lubrication. A lot of work is being done. We are not working on that. Yeah. Yes, Arnav.
Thank you so much.
Yeah. Any other question?
Sir, I guess we are running a bit late out of time. So,
okay.
If there are more questions, can we just mail you, sir? So
yes, you can do that. And if you want to ask, you can ask. I have no problem. I can spend a few more minutes. Otherwise, you can mail me.
Yeah, sir. We'll just mail you, sir.
Okay. Okay.
So, sir, thank you so much for coming for the RSD. And it was actually truly enriching and inspiring session. And we are hoping to bring you back for other sessions, other programs organized by IIT Madras. So, thank you so much, sir.
Thank you. It's my pleasure, and all the very best for the remaining events.
Yes,
thank
sir.
you.